Allow me to start off with an apology. I've been doing it wrong for 25 years. For the last 2.5 decades, for a quarter century, I haven't been teaching mass and weight correctly. I'm ashamed about that. It's not a good thing. There's a major piece that I've been missing. It's not that I've taught it badly. It's just that there's this huge thing that and let me just apologize for all your physics teachers and all your physics textbooks, because they've all done the exact same stupid thing that has led to your confusing mass and weight. So let's fix it today. Let's get this done. One thing I've been doing wrong my entire career. Let's learn physics. If you're in my class, hopefully, by now you understand that when you go to the doctor's office and you stand on the balance, you're actually measuring your mass. And when you leap aboard a scale in your bathroom, you are measuring your weight. So we already know that scales are for weight and balances are for mass. We already know that this thing is really a scale, even though it's called a balance. Units are correct, newtons and dynes, but it's a scale. And this is a scale also, but the problem is it has measurements of grams on it, and those are mass measurements and shouldn't be measured on the same device on which you measure the weight. You also know, if you're in my class, that in the ridiculous English system, that if you stand on a scale, you'll get your weight in pounds force. And if you go to the nurse's balance, you'll get your mass in pounds mass. Okay. Sea level, we have this unit, pounds mass, that is the same number as pounds force, but if you take these two devices and go to the moon, this thing reads 1/6 the number in pounds force, and this one reads the exact same number in pounds mass, contributing to the confusion. We have two different devices in the English system that measure with the same units. It's ridiculous, but we understand that here in this class. We also know that on the elevator, the balance measures the exact same value, but the scale changes. We have even in this class spent time with the proper W equals mg, where weight is in newtons, mass is in kilograms, and g is the gravitational field strength in newtons per kilogram. Here, it's about 10 newtons per kilogram. And we've spent time with a chart like this, where you've given the mass, find the weight, given the weight, find the mass. We can do this kind of stuff. It's not these things that are the problem. We even spend time in this class doing W equals mg for different gravitational environments, where the gravitational field strength on the moon is rounded off to 2 newtons per kilogram. And on Mars, it's 4. And on Venus, it's like it's our sister planet. And moon, really? Isn't that about the dumbest name for a moon? We fill out a chart like this, and chart's empty except for these things, and then I give you use your mass. Then you're like, oh, the mass is all the same no matter where you go, right? Then you multiply by the gravitational field strength of each of the individual places. Multiply by 10, multiply by 2, multiply by 4, and multiply by 9. We do this in class. So what's missing, you say? You know what's missing, and it's the most significant thing? An arrow. Yeah, I made this, by the way, just for this demonstration. An arrow. Why do we not put the arrow on the weight? I don't know. Mass is not a vector. That thing doesn't get an arrow. But I know perfectly well in my own brain, and all the authors and all the physics teachers know perfectly well in our own brains, because the books have brains, that this thing has a direction. But we don't put it down. There's like not a single problem solution where we had to put down the direction of weight. We don't put arrows after weight, and we should. So what should this look like? This. Down, 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 down. Simple arrow. Every single time. Now it's not just units and numbers and scale versus balance and all that important stuff. But weight has a direction. Here on Earth, in our English system, our mass is measured on a balance at 220 pounds mass. That's me, pounds mass. And you can say pounds mass. And the weight would be the same thing. You're standing on a scale, it would be pounds force. How do you differentiate? With that arrow. This. That's it. That is the key. And that is the one thing that we have never taught you correctly. So from now on, Every single time you see a weight, you're going to put an arrow. Every single time I write a weight, and you're going to have to remind me because I'll forget. So just stick your hand up and go, hey, arrow. From now on, I expect all textbooks and all physics teachers to be doing it right because there's an arrow. And this weight is a vector, and the mass is not a vector. That's the major distinction. Please accept my sincerest apology. I'll try to fix it. Let's get this done. Now we're done. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.